In the first screencast for this chapter, we reached the point where we were talking about the equilibrium constant K and what it means. If K was bigger than 1, then that means that you have more numerator than denominator. And of course, in the numerator, you have the products, the denominator, you have the reactants. We also said you can get some really huge numbers like this one right there, which in a sense would be a reaction that goes all the way to the right or to completion. And of course, that would be a good thing, because if you look at the reaction, if it did not go all the way to the right, or if the reaction went very far to the left, all the water in the oceans and lakes and rivers would be decomposing into hydrogen and oxygen, which would make a very, very combustible atmosphere. And when the atmosphere blows up, of course, you hate it when that happens. And then we comment on the fact that you can get some very, very small values of K as well. If K is less than 1, then the denominator is bigger than the numerator, and that means you've got more reactants than you have products. And therefore, it is reactant favored. Now, you can also have K equaling 1. And when K equals 1, you would think, now that's pretty unusual, that's pretty rare, that looks like it's kind of artificial, it's like someone jerry-rigged and set up the experiment to just come out to be that way, and you'd probably be right. That would be an example where the molarity of the reactants just happens to be the same as the molarity of the products. Now, what if you're not at equilibrium? We're down here now. If you're not at equilibrium, or you don't know whether or not you're at equilibrium, you can still create an equation that looks like the equilibrium constant expression, but since you're not positive about whether you're at equilibrium or not, we'll just call it Q. Q here represents the quotient. Remember, the quotient is what you get when you divide something by something else. And so when we do the same thing we did with equilibrium constant expressions, and we get this value of Q, all we need to do is compare the Q to the K. And that gives us a lot of good information. So if we're calculating the value of K, we have to assume that the molarities we're given in the problem are indeed the molarities at equilibrium, or the molarities in the last row on the ice chart. If we don't know if the molarities are at equilibrium, or we're not told ahead of time that this reaction is at equilibrium, then we have to assume that it's not, and we're going to calculate the value of K, and then we compare. So first of all, down here, if Q is not equal to K, we know we're not at equilibrium. Not only that, depending upon whether Q is bigger or smaller than K, we can predict which way the reaction needs to go in order to reach equilibrium. Do I need reactants to continue to revert into products, or products to revert back into reactants? And so if Q is less than K, that means I don't have enough numerator. If I don't have enough numerator, I need more products, because products are in the numerator, which means the reactants have to become smaller, and they're in the denominator. By the same token, if Q is greater than K, then we are past equilibrium, meaning now I have to have some of my products in the numerator turn into reactants in the denominator, so that the numerator gets smaller and the denominator gets bigger. Now, if you look at this illustration right here, where we have two isomers of butane. We have the normal isomers of butane and the only isomer of butane, so it's called isobutane. And if we look at an experiment involving them and we plug our molarities in, notice that we almost get a value that is equal to 1 for Q. And we shouldn't be too surprised here, because both isobutane and butane, they have the same molar mass because they're isomers, and their structural difference is different, relatively minor perhaps. So you might actually get a situation where the concentration of the reactants equals the concentration of the products. If we look at this example problem right here, we have nitrogen dioxide in equilibrium with a colorless gas dinitrogen tetraoxide. and you're given the value of K. You also specify the temperature, it's room temperature, but again, we're not going to use the value of K in our calculations. So the first thing I do, and I always follow these steps, step number 1 is I write the equation. Step number 2, then I like to write the expression based upon the fact that products go in the numerator, reactants go in the denominator, and my coefficient of 2 becomes an exponent. Then part number 3 is where I plug my numbers that I have, my measurements, into the equation. And then part number 4 is where I complete the math with my calculator likely and draw the correct conclusion that my value of Q is smaller than my value of K, and therefore I'm not at equilibrium, point number 1. And number 2, in order to get to equilibrium, I need more products, I need less reactants, so the reaction is going to go to the right. Now, another type of math problem is where we're simply trying to find the value of the equilibrium constant. And so if we have this equation right here, there's my equation, 2 to 1 to 2 ratio. Number 2, I write down my expression. Here's the expression. Notice I have to make sure I've got 2 exponents to go with my 2 coefficients. Step number 3, I plug my numbers in. And step number 4, I can find the equilibrium constant expression. We weren't asked to compare it or see whether or not we were at equilibrium. Now, the use of this value of Q is more commonly found this way or used this way. You will be given the information on your initial quantities, and you're going to be given the concentration at equilibrium of one of the products, and everything else can be inferred, can be deduced from doing your math. So if we take the equation way up at the top of the page, and there's step number 1 is the equation, step number 2 is the expression, step number 3 is where I do my ice chart, which gives me a place to plug my numbers in order to find the numbers that have to be plugged in. And what you're given, and I'll get a different color for what you're given. And let's go ahead and use green for that, because G and given begins with the letter G, and green begins with the letter G. So you're given this. You are given this value. You're given this value. And what a lot of people forget about is you're also given this value. At least it's implied, because you're at the very start of the problem. And then the other thing you're given, if we go back and check the information, is that you have your initial concentrations of your sulfur dioxide here and your oxygen there, and then your sulfur trioxide at equilibrium is right there. So when we go to find out what we're given, I think this is down here. Once we know what we're given, now we can calculate to find out the things that I need to know. And of course, what I need to know is that and that. Notice my stoichiometry is a 2 to 1 to 2 ratio. Notice that my reactants are diminishing, my product is increasing. And so I have an equation here that 0 plus 2x has got to equal that value, and that's a very simple equation. In other words, what we're saying is 0 plus 2x equals 0.925, so my value of x is going to be 0.925 divided by 2. And then we can subtract that value, which we do right there, from my initial molarity of oxygen, and we can subtract 0.925, the 2x, from 1 molar, the initial molarity of sulfur dioxide, and now we have all 3 of the values I need to plug into my equilibrium expression, which is what we do right here. And notice that the number 2 shows up in terms of stoichiometry, and it also shows up here. Notice that when it shows up in terms of stoichiometry, it shows up because it's required there by law. By physical law, demands a 2:1:2 ratio. But it shows up as an exponent by invention, by our choice, by our decision that equilibrium expressions, the coefficients will automatically become the exponents. But you need the 2's in both places. You need it in the ice chart in the middle row where you need the stoichiometric ratio, and then you need it in your equilibrium expression right here in the exponents. Let's look at another example. We have an aqueous solution of iron 3 ions. So this is a net ionic equation with the spectator ions missing. In a reaction with iodide ions, and in that reaction, if we were to sign the oxidation numbers, we have a +3, and here we have a -1. And then when we come over here, my iron is a +2. And over here, we've got 3 iodines with a -1, so this is kind of like a -3rd, which is kind of weird. But you can see that my iron is being reduced. This is a bit of a review because it's going down, and the iodine is being oxidized because it's going up. Now, be that as it may, we have a 2:3 to 2:1 ratio in the net ionic equation. What are we given? We're given the molarity of my iron, or my ferric, which is the old Latin name, my iron 3+ ions, and we're given the molarity of my initial concentration of iodide ions, and then we are also told that the concentration of the I3- is right there, and that is at equilibrium. So once we've analyzed that, and following my steps, step 1, write down the equation. Step number 2, I always like to do next, is I write the equilibrium expression so I know what I'm looking for. Step number 3 is the ice chart. And so what I'm given is I'm given this, and let's underline it instead. So I'm given this, given that, given that, given that, and double check. This is 0.0866, we're given that. So once we know what we're given, we can calculate what we're missing. In order to go from beginning to end here, I'm going to have to increase by 0.0866, which means because this is 2x, I'm going to have to increase by 2 times 0.0866. And because this exponent is 3, I'm going to have to subtract by 3 times 0.866. And because this exponent coefficient is 2, I'm going to have to subtract by 2 times 0.0866. And once I do that, I can get my final results. I need that, I need that, I need that, and I need that. And now I'm ready to plug them into my expression. And again, the coefficients become the exponents. You see it there, you see it there, you see it there. Kind of messy to do on the calculator. And now we grind out the math after we plug it in, which is my final step, and I come up with my equilibrium constant expression. Now, what if my concentrations are measured in pressure because all my reactants and products are gases? Well, nothing really changes here. When we look at this equation, you'll notice we have a 2:2:1 coefficient ratio. So my first step is to write down the equation and make sure it's balanced. Then our second requirement, for me at least, but you can do it in any order you want, of course, I like then to write down the equilibrium expression, my EXP. And then my third step is usually to write down the ice chart and what we're given. We're given that, and that. And now we can do the math. We have to increase, x is going to be 0.020. So 2x gives me 0.040 minus 2x is going to give me 9.96. Then I can take those values and plug them into the equation and grind out the math, making sure I have my exponents that came from the coefficients. And now I have my Kp instead of my Kc. That's my equilibrium constant expression for this equation where all the reactants and products are gases. All right, let's look at another problem real quickly. And this time we are going to be given the value of K right there. First thing we do, if we're not given it, is calculate the equation. For example, on an AP test, they might not tell you the products. They might assume that you know how to write this balanced equation. It's a 1:1:2 ratio. And then let's see what we're given here. You're given the temperature, which is not needed in the calculations. You're given, again, the molarity of each of your, not the molarity directly. This is a little tricky here. Notice that you're told you have 1 mole of hydrogen gas and oxygen gas, and it's in a 1/2 liter flask. So that's going to change the numbers that I put into my ice chart. When we go to analyze our results down here, step number 1, write down my equilibrium expression. Of course, this time I know what K is. In the previous problems, you didn't know what K is, but you knew what the molarities were, one either directly or indirectly. This problem, you know the K, and you're not going to know at least one of your molarities directly or indirectly. So it's the reverse, if you will. So step number 1, the equation. Step number 2, you write the equilibrium expression, which is right there. Here's the equation rewritten there. Now we're going to use the ice chart in order to see what our molarities are going to be. And in order to do that, we know what we're given. Let's put down what we're given. We are given this, and we're given this, and we're given this. Okay? And so we know that that's how we calculate our molarity. So indirectly, we're given the molarity and the molarity of my initial reactants. And now, when we go to do our calculations, we don't know how much we're going to go down by because we're not told the values of any of the molarities at equilibrium. So we're just going to use the letter X to be how much the reactants are reduced and how much the products are increased. We're going to go down by X. We're going to increase by 2X because of the coefficient of 2. So that means in the end, I have this molarity for hydrogen gas, this molarity for iodine gas, this molarity for hydrogen iodide. Even though it's a minus X in there, we just proceed as normal. And now we're going to plug it in to my equilibrium expression. And when we plug that in down here so we can get ready to grind out the math, we get an equation that looks like this right here. Now initially you're going to say, boy, that looks kind of complicated. You see the binomial in there and you say, oh no, am I going to have to use a quadratic equation? But then you realize all you have to do is take the square root of both sides. So that's kind of nice here. Let me erase the box. we're just going to take the square root of both sides, square root of that, square root of that, and when we do the math, we find out our value of x is 1.58, and then we can just plug it back into my 2 minus 1.58 that you see up there, and now we have the final molarities. Now, just as a rule of thumb, if you have any suspicion you might be wrong, you can plug those molarities back into your equilibrium expression, solve it for K, and see if you actually get 55.64. Now, I mentioned the quadratic equation. Okay, what if we actually do end up with a quadratic equation? Are we stuck using it? And the answer is maybe so. Let's see. Here we have phosphorus pentachloride decomposing into phosphorus trichloride and chlorine gas. So there, step 1 is my equation. Step 2, in my way of doing things, is to write down the other thing I'm trying to go for, and that is the equilibrium constant expression. So step 3 would be this ice chart. You can call it step 2 if you'd like. And what are we given? We are given this value, this value, this value, and that's it. So, and of course, we are given the value of K up there. So now, when I do my math, we have a 1-to-1-to-1 ratio, so I'm going to go down by x, I'm going to go up by x, I'm going to go up by x, and so the numbers I plug into my equilibrium expression is there, there, and there. So let's go ahead and plug those numbers in up here. And now we get this expression right there. And we're going to solve this equation for x. Now, when we solve this for x, we get a quadratic equation. And yes, you can use a quadratic equation. If I can even remember what it is, a equals the square root of, let's see, 2b minus 4ac or 2a or something like that. Boy, it's been a while. And you can use that. You might have it programmed already into your calculator and plug in your coefficients of 1, 1.2, and a negative 1.92. And you can come up with the molarity of 0.91 molar for the molarity of your two products. Now, is there an easier way? Because you're taking an AP test and you're in a hurry, you don't have a lot of time. Is there an easier way? And the answer is most definitely, and I would recommend you use the easier way. And incidentally, most of the time, the easier way, the shortcut, the simplification will be successful. Because most of the time, the equilibrium constants are really, really small. And you'll see how that plays into everything in a minute. So let's look at this next problem here. Part 1, equation. Part 2, equilibrium expression. Part 3, ice chart. What are we given? We are given this molarity and this molarity. We are not given anything else other than the value of K. You always get, or you should get, the temperature, which you're not going to use. Now we do the math. We subtract x. We're going to subtract 2x because it's a 1-to-2 ratio. And now we can plug our numbers into the expression. Here's my value of K right there. And notice this 2x has to be squared. Remember that the 2 here is because of the stoichiometry. That's the physical law. The 2 there is by definition. That's the human decision to create an equilibrium expression where the coefficients become exponents. It shows up in both places. Don't forget that. And now we need to solve for x. Now again, you could get a quadratic equation again because you've got this binomial down there. Or you could say, well, look at this value of K. That is very, 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 very small. It's so small that I can expect the numerator that value right there, to barely increase at all. That numerator is not going to get much bigger, which means that the amount of my reactant down here it's got to be very, very small, and my initial molarity isn't going to go down by much. Maybe in the thousandth or 10,000ths place, but you notice that 0.45 only has 2 sig digs, or significant figures. And chances are the value of x might be somewhere way, way, way down here. So in other words, when you take 0.45 and you're going to subtract your value of x, which is 0, 0, 0, x, whatever, you're still going to get 0.45. So let's just ignore the x down here. We can just ignore the x. I'm going to cover it so you can't even see it. And now my equation looks like this, and this is a lot easier to solve for. And if we continue to do the math and solve for that, you're going to see that the answer we get is very, very similar, especially since we only have 2 significant digits to work with, to what you would get with the quadratic equation. So, what's the rule of thumb? When can we take this simplification and ignore the amount of reactant that becomes product? And the answer is right here. It's very simple. Anytime you have your value of K, which is especially when it's real small, you multiply it by 100. If that answer is still smaller than the molarity of your reactant, then you can ignore the minus x. And most of the time, your value of K is not going to be something like some number times 10 to the minus 1 or even 10 to the minus 2. There are a few relatively insoluble salts or compounds that you might have a minus 1 or minus 2 there. Remember, most of your things that split up in water, either they really split up or they really don't split up. There aren't too many in between. Remember what we used to talk about in terms of solubility? If more than 1 gram per 100 grams of water dissolves, we say it's soluble. And if less than 1/10 of a gram per 100 grams of water will dissolve, we say it's insoluble. And the partially soluble in the middle, there's not many like that. So you're not going to get too many of those values. But be on the lookout for them as someone trying to throw a curveball at you. So if we take a look at this problem right here, my equation, my ice chart, I'm given this, this, and this. Now I'm going to do the math, remembering I need my stoichiometry of a 1:1:2 ratio, minus x, plus 2x. I'm going to take those values, I'm going to plug them into the equation, and I'm going to get this for my expression with the numbers in. Now I'm going to say, can I ignore the x? Will the x be to the 1,000th or 10,000th or 100,000th place and therefore not even show up when I subtract it and round off to 2 sig digs? And so we do the test. We take 100 times k. And when we take 100 times k, instead of 10 to the minus 5, we get 10 to the minus third. And 10 to the minus third is still smaller than 8 times 10 to the minus 1, and still smaller than 2 times 10 to the minus 1, so we can ignore the x. It's getting close, but we can ignore it to 2 sig digs. And now I can go through with the problem and find my value of x, so I can subtract it from my 2 original molarities to get my final concentrations. And you can compare that to what you would have gotten if you used the quadratic equation. And I'm going to stop right there, and we will finish this up in a final screencast, hopefully.